So let's take a look at this example problem here. You can see from our diagram on the left, we kind of have this four-leaf clover pattern over here, where for this specific example, we're just going to be looking at this top leaf right here. And within this diagram that they give us, we can see, okay, there's some radius here from our center point down here, some angle theta off this vertical line. And r is going to be defined by this given relationship here, that r is equal to 5 times the cosine of this 2 theta, again, that angle from the vertical there, in units of meters. They also tell us in the problem statement that our theta dot is going to be equal to 3t squared in radians per second units. And our initial condition here, our theta naught, is equal to 0. Now, what are they asking us to solve for? Well, they want us to find the velocity and the acceleration when this theta term here is equal to 30 degrees. They give us a little bit of a hint for this problem here, and they tell us that we're going to apply the chain rule to determine our r dot and our r double dot, and then evaluate at theta is equal to 30. So now that we've had that opportunity to read through our problem statement, understand what they're giving us, what the given diagram is, and what they want us to solve for, the next step is to create our setup page. Now within the setup page, we want to clearly define what's given, what are we solving for, and the assumptions in our plan of attack. So all this right in the first page. We know that they give us this relationship for this r position based off the equation of 5 times the cosine of 2 theta in units of meters. They tell us our theta dot is equal to 3t squared in units of radians per second. Our initial condition, theta naught, is at 0 degrees. And our end unit position here for theta is equal to 30 degrees. I'm going to do that conversion because everything else has been in radians up here. So this 30 degrees is equal to pi over 6 radians. So again, the setup page is a great opportunity to take a look at all your units and make sure everything corresponds correctly. And even do any conversions you need to do right here. So as you reference back to this setup page, you can just plug and chug for your solution. Now, what do they want us to solve for? They want us to find our velocity and our acceleration. So, first thing we want to do is to integrate this expression they give us for our theta dot, which is 3t squared in radians per second here, in order to get our theta, because we don't have our theta here yet, and we need to solve for that. So, theta is equal to, now we take the integral with our limits of integration from t0 equals 0 up to some final time t of our theta dot dt. Now we know our relationship for theta dot dt. We go back up to the setup page here. Theta dot is equal to 3t squared. Plug in this here. So now we have the theta is equal to the integral from 0 to t of, now, we plug this in here, 3t squared dt. We can do out this integral here. Pretty straightforward calculus there. The integral of 3t squared ends up being 1/3. Bring that down in front there. The 3 cancels with the 1/3 on the bottom. T cubed. So theta is equal to t cubed. So now, if for the condition that they give us in the problem statement, we have that our theta is equal to 30 degrees here. So now we can start plugging back in here. Theta is equal to t cubed that we just solved above there. So t cubed now from this here is equal to 30 degrees. So from this, we can back out our time value. So first thing we want to do though is realize, okay, we're dealing in radians per seconds and radians. We need to get from degrees to radians. So we've already done that conversion up top here. This is pi over 6. So t to cubed is equal to pi over 6 for 30 degrees there. We can rearrange, take the cubed root of both sides, solve for our t. T is equal to the cubed root of pi over 6. Take that relationship there, plug this back in to get our theta. So we have our t value here, plug that t value in right here back into our theta dot term up here, which is 3t cubed, and then we can get our theta dot value there. So we take this out, plug this into a calculator, numeric solver, t is equal to 0.806, plug that in there. We end up with, now we want to solve for theta dot. Theta dot is 3 times that 0.806 squared. So now we have a value for our theta dot term of 1.95. Again, pay attention to our units here, radians per second now. So the next step in our solution here is to solve for the derivative of theta dot to get our theta double dot term. Because what we know is we're looking for in the end here our velocity v, our acceleration a. And in order to solve for those, we're going to need to know theta, theta dot, theta double dot, r r dot, and r double dot. So in the beginning here, I'm just solving for all of those, get as many of these as numeric values as I can. So when we get to the end, it makes for a less complicated equation. We can just plug in straight numeric values as we're solving. So with that said, the next step along the way is to solve for our theta double dot, which is the first time derivative of our theta dot term, which is given to us as 3t squared. Take that derivative, theta double dot now becomes 6t. Well, we know a value for t. We just solved for that in the previous page. T is equal to 0.806 seconds. Plug that back into my expression for theta double dot. Theta double dot is equal to 6 times that value for t. Plug and chug. Theta double dot then becomes 4.836 in radians per second squared. So now I do have a value for my theta, theta dot, and theta double dot. So I can go back to my original expression for r here and start plugging in my known values. So r is equal to 5 times the cosine of 2 theta. Well, I can solve for r numerically because I know my value for theta is 30 degrees. Plug that in there. 5 times the cosine of 60 degrees. Again, be careful. We're now in degrees, so make sure your calculator's in the right mode. Could have converted to radians as well if you've wanted, but I left it in degrees here. We can plug and chug, and then we get our value for r is equal to 2.5 meters. So the next thing we want to solve for is our r dot, our first time derivative here of r. So I take the derivative of my expression for r. So derivative of 5 to cosine of 2 theta becomes negative 10 times the cosine of 2 theta times the derivative of what's inside. Derivative of theta is theta dot. So this gives me a negative 10 times the sine 2 theta, where my theta is 30, becomes the sine of 60 degrees. I have a value from a theta dot that I previously solved for of 1.95 in radians per second. Again, pay attention to your units. Do that all out, plug and chug, plug into numeric solver. We end up with our r dot is equal to negative 16.88 in units of meters per second. So now I have r and r dot as numeric values. I want to get my r double dot because I'm going to need that again to solve for velocity and acceleration as we move forward with the solution to the problem. So to get our r double dot, we take the first time derivative of r dot, or the second time derivative of my r expression there. So if I take the first time derivative of my negative 10 sine of 2 theta times theta dot, I go through here, take that derivative, and what we want to do here now to do that is recall our product rule. So if we recall our product rule here, what we want to do is take the derivative of the first expression times the second expression plus the first expression times the derivative of the second expression. So derivative of the first expression here, here's my first expression number 1, here's my second expression here number 2, right there. Take the derivative of the first one, take the derivative of negative 10 times the sine of 2 theta times second, which is theta dot, plus the first, negative 10 sine of 2 theta, times the derivative d over dt of the second theta dot. So that's my product rule there. I can do that out, plug and chug, take that first derivative of my negative 10 sine of 2 theta. It becomes negative 20 times the cosine of 2 theta times what's in the inside. Derivative of 2 theta becomes theta dot. So theta dot times my theta dot is a theta dot squared. So there's the left-hand side of this expression of the product rule. Now we deal with the right-hand side. So I have the first negative 10 times the sine of 2 theta times the derivative of theta dot, which is theta double dot. That's pretty easy and straightforward. So now I look at this, I've got a theta dot, and a theta double dot in here, all to get my r double dot. But I now, from how these above, have values for those. I can plug in my theta of 30 degrees, becomes 2 times 30 is 60 degrees. My theta dot of 1.95, I got squared there, and my theta double dot that I solved for up here of 4.836. Radians per second squared, radians per second degrees. Make sure we pay attention to our units. Plug and chug. We end up with our r double dot having a numeric value of 80 meters per second squared. So now I know that this is kind of now all scattered across the first 2 pages and a little bit disorganized. So what I'd like to do is stop for a second, move everything into one location here at the bottom of my page. I'll move this up for you to see. So what do we know? What have we solved for? So I write down everything we solved for in one nice, neat location that I can reference back to as I go through and then complete the solution for velocity and acceleration V and A. So we know that at theta is equal to 0 degrees, that gives the problem statement, we have a time, 0.806 seconds that we solve for. I've solved for all my r dot, and r double dot, my theta dot, and theta double dot, as numeric values in units of meters, meters per second squared, radians per second squared. All my units are correct. I have numeric values for all of these, so now I'm ready to start plugging into the next step of the solution. So now what I want to do is I'll leave that table up there that I just found all the values I've solved for ready and able to reference back to. So the next step is to solve for the two things I asked for in the problem statement, our velocity and acceleration. Let's do one at a time. Let's start with velocity first. So the first thing we want to do is go back to our textbook, and we recall that we do have an expression for velocity we've seen before and in previous courses, that our velocity term here is given to us as r dot, unit vector in the use of r direction, plus r times theta dot times the unit vector in the theta direction there. So I have this expression now here that I can start plugging into. Well, I have a value for my r dot now that I've already solved for it. I can simply look up above here, my r dot, negative 16.88 meters per second. I can plug that right in there. I have an r value of 2.5 meters. I can plug that in right there. And I have a theta dot value here of 1.95. So this is why it makes sense to have everything, one, pre-solved for in advance so I can plug and chug, and two, in a nice, neat, and organized manner so I know right where to grab it, not sifting through pages and pages of calculations to get to it. Plug those all right into this expression for my velocity here, and I have this as a vector value here, so negative 16.88 in the r direction and 4.87 in the theta direction here. Well, if I want the magnitude of that, then what I would do is take the square root of the sum of the squares of the individual components. So I do that out there. Rather than being in vector form, I can get it here, take the magnitude. So velocity is equal to the square root of 16.88 squared, negative 16.88 squared plus 4.87 squared. Our velocity value here, magnitude, is 17.57 meters per second. So from there, let's do the second part of what they asked us to solve for in the problem. That's the acceleration. So again, I'm going to move this right here so we can easily see everything. So now I have all of my values here. We'll slide this up just slightly. So there we go now. So with this here, I can still see and reference all of the values that I'd solved for previously. And I have my general equation here now for acceleration. A little bit more complicated here. A few more variables we need to plug in for, but we have numeric values for all of these. So as you recall, our acceleration vector equation is equal to our r double dot minus r times our theta dot squared in the r direction, plus our theta double dot plus 2r dot theta dot in the theta direction there. So we have the two components, our r components and our theta components here, but we know all these known values. Our r double dot, we look up here, negative 80 meters per second squared. Our r, 2.5 meters. Our theta dot, we can go back up here, 1.95 radians per second. So that takes care of this whole side over here. Now we can move the right-hand side, our theta side of the equation here. So our r, again, is 2.5 meters. Now we have our theta double dot term of 4.836. Plug that in there. Plus 2 times our r dot. Our r dot is negative 16.88. Plug that in there. And we have our theta dot term here, again, of 1.95. Plug that in there. All numeric values, plug and chug. Excel, MATLAB, Python, calculator, whatever your favorite is, you can use that, plug it in. Again, first thing we do is we get this in vector form. Now, the problem statement had asked us, please provide the acceleration in vector form. Please provide the velocity in vector form. This is as far as we need to go. They just said find velocity and acceleration. So I'm going to err on the safe side here and solve it both ways. I've got my vector notation here. Then I've also taken it one step further and solved for my magnitude. So I do that there, square root of the sum of the squares. Square root, we do our math out here, of negative 89.5 squared plus 53.7 squared. Our acceleration value is now 104.4 meters per second squared. And those are the two things that they'd asked us to solve for, our velocity and our acceleration for this problem here, with the correct units as the magnitudes.